Okay, so part 7 is going to be about another processes can be done to the metal after the casting, which is going to be about the sheet metal working. Um, you remember that we did in week 3 an induction about the sheet working in the lab, and it's going to be something similar to the processes that we done earlier. So the sheet metal working can be classified into cutting operation, bending operation, the drawing operation, and same drawing. We had the drawing for the bars. Other sheet metal forming operations, dies and the presses for the sheet metal processes, sheet metal operation not performed on the presses machine, and then the bending of the tube stock. So again, I divided this section into 3 different slides, and I'm going to start with the first one. So in this one, we are going to define the sheet metal working as the cutting and deforming operations performed on the relatively thin sheet of metals, where the thickness of the sheet metal is going to be about 4 millimeters to 6 millimeters. The thickness of the plate stock is going to be anything above 6 millimeters, and operation usually going to be performed as a cold working. The sheet and the plate metal parts for consumer and industrial products such as the automobile and trucks, the airplanes, the railway cars, and the locomotive, making the ducts, making the water tanks, all can be done by the sheet metal working operation. The advantage of the sheet metal parts are first, we're going to achieve high strength and good dimensional accuracy, good surface finishing, relatively low cost, and economical mass production for the large quantities. Just imagine how many car doors we make in every year, how many refrigerator body we make in every year. Okay, so all this stuff has been done by the sheet metal parts. The sheet metal working terminology is going to be using the punch and the die tooling to perform the cutting, the bending, and the drummings. Also, we can have the stamping press, which is going to be a machine tool that performs most of the sheet metal operations in the industry. And we have the stamping where the sheet metal products can be made by this process. And I'm going to send you some videos similar to that. The basic types of the sheet metal process is going to be doing the cutting by using the shearing to separate the large sheets like the gluten you found in the lab. Also using the metal scissor. So it's going to add 2 opposite direction forces that add a shear force to make the part separate. We do have the blanking, which cut the part perimeters out of the sheet metals. And we have the punching, which is making holes in the sheet metal. For the bending, we're going to be straining the sheet around the straight axis. And you remember how to do that. We have the drawing, which forming the sheet into a convex or concave shapes. So we start with the cutting operation, and you can see this is the procedure, how it's going to be done. So once again, we have the punch and the die. Okay, where's the pen? Okay, sorry, I choose the wrong device. We have the punch and the die. Okay, the punch and the die. So we're adding the force in one direction while the die is going to be stable, and then the contact will start. We start to have some plastic deformation to be occurred. We keep doing the work. The penetration will be simply going to be increased until we're going to reach the point of the failure. Okay, you remember when we're going to have the ultimate stress, and then we're going to have the failure to occur. Same thing here. So this failure will cause a fracture, then the parts going to be separated. So the figure 1 is going to be just before the punch contact the work. The second one is going to be punch pushes into the work, causing the plastic deformation. The third one is going to be the punch penetrates into the work, causing a smooth cut surface. And finally, figure 4 is going to be a fracture is going to be initiated at the opposite cutting edges to separate the sheet. So we have 3 principal operations in the press working that cut the sheet metal, which are the shearing, the blanking, and the punching. So we start with the shearing operation. You can see on the left side, the side view of the operation, and the figure B is going to be the front view of the power shear equipped with the inclined upper cutting plates. Now the reason after this enucleation is so we can maximize the force to be at small area, so we're going to have a better effects for the cutting operation. Now the gluting you're going to use in your project is going to be mainly doing that work. The second one is going to be the blanking and the punching. They look the same, but the difference is that in the case of the blanking, the one we have in the figure A, the sheet metal cutting to separate a piece which called the blank from the surrounding stock, that this blank is going to be used later in further operations. In the case of the punching, it's similar to the blanking, but the cut piece is going to be a scrap, and this will be called the slag. So the slug is here, but the part itself has a hole in it, and that's the whole thing about the punching operation. So you can see here on both ends, we have the blanking, and we have on the right is going to be the punching to make multiple holes by using multiple punch on the plate. So we always need to consider that we should have a clearance in the sheet metal cutting, which is a distance between the punch and the cutting edge and the die cutting edge. Okay, so that will be the clearance. The typical values going to be in the range between 4% up to 8% of the stock thickness. So you're going to have, let's say, 10 millimeter thickness plate. That's mean you need to consider something like 0.04 millimeters to be the gap we have here. Okay, the gap or the clearance between the punch and the die. If it's going to be too small, the fracture lines are going to be past each other, causing the double positioning and the larger force. If it's going to be too large, in that case, the metal is going to be pinched between the cutting edges, and the excessive burr will result. So that's why we need to have a good calculation for that. How to decide that? Mainly is going to be done by trial and error. We have the angular clearance because if I would like to do the cutting of the part here, I don't want it to stuck in the rest of the die. So we need to have an angular clearance, which is going to allow for the slug or the blank to drop through the die freely. Typical value is going to be about 0.25 to 1.5 degree on each side. The punch and the die sizes we have for the rounded blank, usually diameter or the DB, diameter of the blank, is going to be the blanking punch diameter is equal to the diameter of the blank itself minus 2 multiplied by the clearance. Okay, so the blank punch diameter is going to be slightly smaller than the round blank diameter. B is the punch. Sorry, not bunch. The blank diameters. The blanking die diameter is going to be equal to the same diameter of the blank I would like to have. C is the clearance. For the round hole of the diameter of the hole punch diameter is going to be equal to the diameter of the hole I would like to have, while the hole die diameter is going to be the diameter of the hole plus 2 times the clearance. So you can see that the diameters we're going to have here, in the case of the blanking, the punch diameter is going to be the smaller than the larger size, whereas it's going to be the opposite on that direction. So the values we're talking about is going to be here. You can see that this is diameter of the hole, this is diameter of the die, and this will be sheet metal thickness we're talking about. These are the two clearance we're talking about. Okay, so die sizes determine the blank size, and the punch size will be determines the hole size, where the C is equal to the clearance. Once again, we're going to have questions on how to apply these values. Calculation of the cutting forces, which is very important to determining the press size. If I'm going to need just small forces, I'm going to choose a smaller press size. The equation for the force is going to be equal to the S multiplied by the T multiplied by the L, while S is the shear strength of the metal, which is a property of the metal itself. T is the stroke thickness, and the L is going to be the length of the cut edge. So that's the end of the part 7, and I'm going to continue with part 8, and we have another part 9 later.